Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, can we evolve better robots? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week we'll be revisiting two topics that we've covered before: swarm robotics and robot evolution, to find out how we can evolve robots that work together more effectively. But first, I'd like to remind you to rate this episode and leave a review if that's something you can do on the platform you're listening on. And don't forget to share the podcast on social media or tell your friends about it. It really helps the podcast reach more listeners. So, with all that said, I'm excited to introduce this week's guest. I recently had a really interesting chat with Tanja Katharina Kaiser from the University of Technology Nuremberg about how applying evolutionary principles can help robot teams make better decisions. Today, I'm talking to Tanja Katharina Kaiser, a senior researcher at the University of Technology Nuremberg, whose work focuses on adaptive multi-robot systems for solving complex real-world tasks. Hi Tanja, lovely to have you on Robot Talk.
Hi, thanks for having me here.
So you lead the Multi-Robot Systems Satellite Lab. So to get us started, can you give us a little bit of an overview of the research that's going on in your lab?
Yes, sure. So right now I focus a bit on object transport in collectives. So several robots try to transport an object from an initial position and to a goal position that we tell them. And there exist several solutions to that already, but all have some drawbacks. For example, you need to know which object it is in advance to calculate certain trajectories, like the path that it's known how it should go. And this restricts the approach. So we try to make this approach more versatile by using artificial intelligence. For example, vision language models, so models that can understand vision and language, could help us determine what object we do have and how we have to transport it. And then we don't need to know in advance what object it is. So this is one focus we're doing. Then we are also considering, like, how should we approach it if we have a weight distribution that's not uniform, so if parts are heavier or lighter. What can we do? How can we transport that? And so that's the main focus right now that I focus on with my group.
Okay. Yeah, it's one of those things that, like, on the surface of it seems like quite a simple thing to try and achieve. And then as you start to dig into it, it gets more and more complicated.
Yes, especially with the different robots, you always have to consider that you have to kind of make them work together and coordinate them. And that sounds super simple. But then to transfer that to the technical system is actually quite a challenge.
Yeah, I'm sure. So you mentioned like understanding language. So is the idea that, like, you would describe what the object is verbally or in writing?
We would give it actually an image of the object and then some text that describes stuff. And try to get most information out of this. But we are also in the process of trying out what is like the best. Should we get like a description of the object out of one model and put this description into another one? Or is one model able to finish all of this?
Right. Okay. So my background is actually in evolutionary biology, and specifically I studied ants. What you're talking about right now just really reminds me, I was at this conference years ago and they were talking about looking at how ants transport objects together. And they'd got all these different shapes and sizes, blocks of cheese that they'd given to groups of ants, and to see how they like distribute the weight and get it through a small gap or all kinds of things like that. I don't know what my question is, but yeah, you're really just reminding me of these little ants carrying bits of cheese.
Yeah, actually, ants are like a very great example for all this collaborative stuff. And a lot of the research in that area is also looking at like, how do ants do it? And then try to infer or get some inspiration from that. So I also have like one PhD student. He's not in Nuremberg, but at a different university. And he's doing some ant-inspired things for robots, like together with the evolutionary stuff I did before. So we get a lot of inspiration from ants, actually.
I guess the robots have the advantage that they can communicate, assuming you've got like Wi-Fi or whatever, they have the ability to communicate with each other in ways that ants just can't.
Yes and no. So like depending on how you try to set up your system, do you really want to have it like in a way that you can scale it quite big? Then you don't want to rely on a global communication, for example. Or sometimes you have areas that are restricted in Wi-Fi, and then you don't have that. So you need different approaches. And so we try to get like a solution that is kind of decentralized if possible. Like with the language models and stuff, that's a different story there. Decentralization is really an issue. But if we can build a system that is as decentralized as possible, but as centralized as needed, we can at least like ensure that it's also working in areas where we may lose our communication abilities.
Yeah. So you mentioned applying evolutionary principles to multi-robot teams. And this is an area that, given my background, I find particularly fascinating. Can you talk through like how does it work in practice to evolve better robot teams?
Yeah, so with these evolutionary algorithms, it's inspired by natural evolution. So we try this iterative approach like in generations. And then there are different ways to do it. But what I did is like every generation, I tried different robot controllers. So I had a pool of robot controllers. It would be like the DNA or something that's tested per generation. And then I give every member of my multi-robot system the same controller. So it's clones that are there.
Right, okay.
And then I test how well this group of clones works together to finish the task. And this is measured by some fitness function. And also there are very different approaches. We could just reward the task. So if we stick to transporting something, we could say, okay, did it reach the goal position? Or what I also did is like I did not reward tasks, but I just told it, predict your environment well. And then I saw what like collective behaviors emerged. So I let them basically do whatever they liked as long as it was like some collective behavior.
Okay.
That's also an interesting thing. And then like after we tested all of this pool of controllers, like we usually keep the best one so that we don't lose our progress.
Yeah.
And then the other ones are created by mutation. So like switching, for example, the weights of a neural network a bit. And sometimes also by crossover, so combining different genomes. And then this new set is again tested, and then we iterate through this until you reach, for example, a certain fitness or a number of generations is over, and then we look what we got.
Okay. So yeah, I mean, for listeners who aren't familiar with how evolution works in detail, this is kind of mimicking the process whereby like each generation natural selection means that the individuals that do the best pass on their genes to the next generation, and then the world ends up getting filled with organisms that are, good at surviving and filling the world. It's interesting to me. So I've come across a few people who've done evolutionary robotics before with like evolving robot bodies. I don't think I've ever spoken to anyone who's done it with kind of essentially evolving robot behavior. In this case, software, but it's kind of the equivalent of animal behavior, right?
Yes, exactly. I think there are some people doing that, so it's not a thing I invented, but I think it's more interesting for actually people working with multi-robot systems instead of single robots, because for a single robot you have this big pool of machine learning algorithms you can use, like there's a bunch of methods. And for a single robot, it's kind of straightforward to use them. There are also challenges, but it's not about like figuring out who contributed how much to a task. This is a problem in multi-robot systems, because sometimes they do something like pushing an object, and one robot is not doing anything or only pushes.
Not pulling its weight, yeah.
Yeah, so then it's clear. Then it's zero, right? No contribution. But maybe it just pushes at the start and then it stops pushing. But in the beginning, to get it sliding, it needed an extra push. We don't know.
Yeah, that's really interesting.
And then you need to decide who contributed how much with most of the other algorithms. So that's kind of a challenge. And with these evolutionary approaches, we just can ignore that, because it's like this. We just check if the task was fulfilled, and we don't care how much the individual actually contributed in giving the fitness for this behavior.
Yeah. So you said that for each of your algorithms that you were testing, you kind of cloned it and all of the robots had the same algorithm. But of course, in real life, like sometimes diverse teams do better. So I guess that's the next level of complexity. Is that something you plan to do? Have you started doing that?
Yes, with this PhD student I mentioned before, who's also inspired by Ant's behaviors, he actually will study hardware and software heterogeneity. And so because that can also bring benefits to certain tasks, it makes everything but also more complicated. Like, does every robot have a different behavior, or do we just give a subgroup of our team different behaviors? How is then like the fitness? Is it like the same for everyone? How is like the contribution again? So then we run into these problems. I also did some initial tests with like a very simple scenario that was in a simulation, and our robots were basically dots on a grid.
Okay.
So a grid world. And then what happened is that in one half of the grid world, one species existed, and on the other half, the other one. And they did their stuff on each half, but they did not interact. And then I don't have the benefit of like evolving to different behaviors, for example, or to different controllers to get like a bigger behavior where actually robots collaborate that are different. So that's challenging, but it's an interesting thing. So
and like you were saying about like the different contributions that each robot makes, you've got to be careful you don't end up kind of evolving a population of freeloaders.
Yes, exactly.
So you're taking advantage of the process of evolution to try and make better robot controllers. A lot of roboticists kind of skip the process step and just copy things in nature that have evolved, right? And so you can kind of look at the outcomes of real evolution and copy that. What are the pros and cons of those two different approaches?
So direct copying is not that easy. Because like you have to find out how they actually do it, right?
Yeah.
So you may see like that ants are building a nest, but how do they do it? It's not always clear. So it's not super easy to just transfer that. Then also like the sensors, or how like animals perceive their world and our robots perceive their world is different and cannot be like done in the same way easily. And when you have collectives like natural swarms working together, it's also the question, what is the individual behavior and what is the global behavior then? We can't say like from the global behavior, this has to be the individual behavior.
Yeah.
Because there are like these self-organization feedback processes going on where like several robots collaborating brings something bigger than one robot doing it. And so this is a challenge. And then you would need to think a lot, design an algorithm, test it again and again. So basically you're the optimization algorithm because you do it step by step. And then I can just use an algorithm that searches for me the solution, does that over iterations, and I just watch how it emerges from the process without me having to take care of all these these aspects that I don't know.
Mm.
So on the other hand, if I evolve something, I usually use like artificial neural networks or controller structures where I actually can't know what exactly happens. It's a big black box. And then I can't guarantee a behavior.
Right.
I test it. It's somehow likely that something happens, but I don't know if this is really the case every time I execute it.
Yeah.
But it's also like I have one work where I first evolved something, and then I did a study on the evolved behaviors.
Okay.
And from this, I inferred what could happen in there and used it to implement a better algorithm myself. So I learned from the evolutionary process what I could do and used it to implement an algorithm where I then exactly know what will happen.
Yeah, and I was thinking, I mean, obviously, like your initial starting selection of algorithms are not just plucked out of thin air. You've come up with something that might work, that you reasonably think could work, and then you're evolving from that, right? It's not just random.
No. But for implementing an algorithm, yes. For evolving an algorithm, we actually start from random.
Okay. So, interesting.
No.
I mean, that's what nature does.
Exactly.
I guess that gives you the opportunity to come across things that you'd have never thought of yourself.
Yes.
Like totally novel solutions.
Yeah. Yeah. So it's very creative what the evolutionary algorithm sometimes outputs. So.
Yeah. And how long does one generation take, and how many generations are you doing to come up with these algorithms or the final result?
It depends. So if you start like in very simple simulations, like where my robot is a dot and everything is just calculated.
Yeah.
I can run something in 2.5 hours and have an output.
Okay.
But if I go for more complex stuff like realistic simulations, it's rather days or weeks that it runs. Yeah. And on real robots, I would not start. I would then rather pre-evolve something and try to go from there, like to have a starting point, because otherwise it would take probably weeks to test all of this because you can't speed up in simulation. I can just say, run it faster.
Yeah.
And then we don't want our hardware to break in the process.
Yeah. I mean, even a few weeks is still, compared to real evolution, it's pretty quick.
True, but we give it a body already.
Yeah, that's true.
I mean, there were works which I find pretty cool where you combine it, like you have body and brain. So you talk to people who evolved bodies, but you can also combine it, which I find very interesting.
Yeah.
But then it's hard to test in real world because I won't build the body that was evolved.
Yeah, I saw there was somebody who was like evolving different robot legs and like 3D printing them and trying them all out, which was pretty cool. But I don't know how long that took, but probably a while.
Depending on how big the robot is, also the 3D printing already takes a while.
Yeah. So, what applications do you think robot swarms are best suited to tackling right now? And what do you hope to apply them to in the future?
So right now, I would say everything that's related to logistics. We see that already. Amazon was in the news once with this Kiva robot system that transports the full shelf, which is quite cool. And there's still some open issues, like basically traffic jams in warehouses.
Right, yeah.
That are not resolved automatically yet, or only like a limited set of problems is resolved automatically. So this is a very, very good application area, I would say, where it makes sense. And then also you can transfer learnings from that to automotive driving, because if you think of it, that's a multi-robot system, what we have on the streets.
Yeah. Complicated by the fact that some of the cars are still being driven by humans as well.
Yes. And I also wouldn't put my stuff that I do in like a warehouse or in warehouse scenarios right now. I wouldn't directly put it on the street, but I think it's a starting point from where we can go the step further to see methods and things to later on use it and fine-tune it for the applications or extend it for the application of autonomous driving. And in the future, I hope to see it like in basically everywhere. Because when we think about it, in our homes, more and more robots are integrated, and it's not of the same type, like not this homogeneous, everyone gets the same controller thing, but it's like a fully heterogeneous system usually. Or maybe I have 2 vacuum cleaners because I have 2 floors. And I don't know, I have like this companion robot for my child to do homework, and what else? I don't know. Like a different set of robots. And then it would be cool if they could actually interact, and some stuff makes sense. Like after the cooking robot is finished, maybe the vacuum cleaner robot should drive into the kitchen and clean the ground because something may have spilled or dropped or so.
Yeah.
And so I hope to see it basically everywhere.
Yeah. I love the idea of like just a swarm of robots kind of coming into my kitchen and tidying up and sorting everything out behind me. That sounds great.
I would love that too.
I think I'll have to wait a while for that one, but I'm glad to know that people are, if not working on it right now, at least, aiming in the right direction.
Yeah, I think more and more people are interested in having like a lot of home robots, and then I think the step to combining them into a larger system is quite obvious at some point.
Yeah. Tanja, it's been great speaking to you today. I've been chatting to Tanja Katharina Kaiser from the University of Technology Nuremberg. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And don't forget to join the Robot Talk community on Patreon if you'd like to support the podcast and get access to some awesome perks, including behind-the-scenes updates and monthly bonus episodes. Visit patreon.com/Claire Asher to find out more. Next week, I'll be speaking to Jeremy Haddle from the Satellite Applications Catapult about robots in orbit. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.